Different theories of acids. Three most important theories that we use are Arrhenius Theory, Bronsted-Lowry Theory and Lewis Theory. This short video just intends to separate the three theories to make it clear when and why we use them. The usual definition of acids comes from the Arrhenius Theory, and Arrhenius acids are chemicals, compounds that produce free hydrogen ions in solution. This means that the compound either interacts with water or is broken down by water to release hydrogen ions. Now, because it happens with water, it means that Arrhenius deals specifically with aqueous systems. Bronsted-Lowry theory looks at the acidity or acids from the point of view of the hydrogen ions only, but it doesn't require water, which means that it is possible for Bronsted-Lowry substances, Bronsted-Lowry acids, to be non-aqueous. Lewis extends the theory a bit further by considering not hydrogen ions but electrons. So first of all, let's have a look at the Arrhenius idea. Here we see effectively the kind of all-encompassing theory is actually Lewis. If we hover over here, you'll see that Lewis is kind of a broader theory, so it applies to everything. Within Lewis we have Bronsted-Lowry theory, and the red dot here represents Arrhenius theory of acids. So if I click on this, let's have a look at Arrhenius, and this is what we got. So Arrhenius acids are the hydrogen ions in aqueous solution. So when a hydrogen ion is produced, it interacts with water, and we get hydroxonium ions or hydronium ions. So anything that releases these hydrogen ions in solution will be an Arrhenius acid. Let's have a look at the Bronsted-Lowry theory. What we're dealing with? Well, Bronsted-Lowry theory looks at it from the point of view of the hydrogen ion donor. Whichever species donates the hydrogen ion is considered to be an acid. Now the hydrogen ion then goes on and interacts with this picture actually shows H2O, doesn't it? Oh, okay, so this is a reaction between hydrogen and OH minus. So I've made this video and I forgot what I put in there. Hydrogen and OH minus. So the hydrogen ion is being donated to the OH minus, and so whatever donates the hydrogen ion is a Bronsted-Lowry acid. And let's have a look at Lewis theory. Well, Lewis theory looks at this electron pair. Effectively, the electron pair, whatever donates the electron pair, is a Lewis base, and so the species, the H plus that's accepting the electron pair, is the Lewis acid. So in all three Arrhenius, show it here, Arrhenius, Bronsted-Lowry and Lewis, we can all demonstrate the same be demonstrated by the same reaction. Let's go look at it in a little bit more detail. Alright, so Bronsted-Lowry. Bronsted-Lowry theory considers only the hydrogen ions and doesn't specify they have to be in aqueous solution. So in this particular case, we could take an ammonium ion. Ammonium ion is NH4 with a positive charge. Now, if this ammonium ion donates a hydrogen ion, well, it's effectively acting as a Bronsted-Lowry acid. So if we show it donating a hydrogen ion, this can donate a hydrogen ion to any species, and so the ammonium ion then becomes a Bronsted-Lowry acid. Now, if this happened in liquid ammonia, for example, well, it's fine. It's a Bronsted-Lowry acid. Lewis, however, is involved with the electrons. Now here we have aluminium trichloride, which is an electron deficient species. Count the electrons up around the aluminium, there are only 6 electrons. Normally 8 electrons is a full complement of electrons in a shell, so it's missing a pair of electrons. So this species, aluminium trichloride, can accept a pair of electrons. It is a Lewis acid. This species, chlorine, can donate this pair of electrons into the outer shell of the aluminium to fulfill the electron pair requirement. And so here we have the chlorine behaving as a Lewis base. Now, this has nothing whatsoever to do with hydrogen ions or any reaction involving hydrogen ions. So the advantage of Lewis theory is that we can apply it to systems that are non-aqueous and don't have anything to do with hydrogen ions. This means that anything that donates an electron pair in a reaction can be considered to be a Lewis base. So, for example, when ligands attach to transition metal ions, the ligands themselves are Lewis bases and the transition metal is a Lewis acid. And just to remind that Arrhenius is all about free hydrogen ions in aqueous solutions. Right? All aqueous solutions contain water molecules, and water molecules themselves dissociate into hydrogen and hydroxide ions. You can see the process here. Here's a water molecule, and dissociation occurs. This hydrogen ion is then captured by another water molecule to make a hydroxonium ion, and it's this that causes the acidity. In this particular case, the solution would be neutral because the water makes as many OH- ions as it makes hydrogen ions. In fact, there would be, in normal water at 25 degrees Celsius, there would be 1 × 10⁻⁷ moles per litre of hydroxide ions and hydrogen ions.